A perfect hexagon of clouds swirls at Saturn's north pole. We are about to journey deep into the planet's greatest enigmas, from its fleeting ring spokes to an ocean world hiding beneath an icy crust. By the end, you will know 25 of the most profound and unresolved secrets of this gas giant. What force could possibly create a geometric storm larger than our entire planet? And why does one of its moons spew water into the void of space? What do you believe is the most compelling mystery waiting for us in the dark? That colossal hexagon of clouds is just the beginning. Saturn's most iconic feature, its dazzling ring system, presents us with a mystery that has confounded scientists for centuries. The origin of these rings is perhaps the planet's greatest puzzle. They stretch wider than the distance from the Earth to the Moon, yet in some places they are astonishingly thin, no taller than a two-story building. So where did this magnificent, impossible structure come from? The leading theory suggests a violent and chaotic past. Imagine a moon, perhaps as large as the planet Mercury, orbiting Saturn in its youth. A catastrophic event, like a colossal collision with a passing comet or asteroid, could have shattered this moon into countless fragments. Over immense stretches of time, the gravity of Saturn would have shepherded these pieces into the flat, disc-like rings we see today. But this dramatic story has a major flaw. The rings are not made of rock and metal like most moons. They are composed of more than 95% pure water ice, glittering with a brilliant, almost unnatural whiteness. This icy composition is difficult to reconcile with the destruction of a typical moon, which would have contained a rocky core. Another theory proposes that the rings are ancient relics, leftover rubble from the protoplanetary disk of dust and gas that formed Saturn itself over 4 billion years ago. Yet this idea also struggles. The rings are too clean, too bright. If they were truly that old, they should have been darkened and polluted by constant bombardment from meteoroid dust, becoming a murky gray. Their pristine condition strongly suggests a much more recent origin, perhaps within the last 100 or 200 million years, a mere blink in cosmic time. This creates a profound and beautiful contradiction. We are faced with the possibility that Saturn's rings, a seemingly permanent fixture in our sky, are actually a temporary spectacle. We might be living in a uniquely fortunate era, a cosmic window where this giant world wears its crown of ice, a mystery born from either a recent, unimaginable destruction or a process we have yet to even conceive. But the rings are not the only geometric marvel in this system. High above Saturn's north pole, a perfect hexagon of clouds has been churning for decades, a storm of such immense scale and precision it defies all earthly logic. This six-sided jet stream is not a fleeting formation. It was first glimpsed by the Voyager probes in the 1980s and has remained stubbornly stable, watched continuously by the Cassini spacecraft for over a decade. Its sheer size is almost incomprehensible, with each side longer than the diameter of our entire planet. You could fit multiple Earths inside this colossal atmospheric pattern. How does a fluid, chaotic environment like a gas giant's atmosphere produce and maintain such a sharp-angled, geometric shape for so long? Scientists have turned to laboratories on Earth for clues, creating rotating fluids to simulate Saturn's conditions. In one experiment, a circular tank of water was spun at different speeds, and as the fluid moved, a stable hexagonal pattern emerged at its center. This suggests the hexagon could be a type of standing wave, a stable pattern created by the interaction between different layers of the atmosphere spinning at varying velocities. It is like a cosmic version of a vibration creating a pattern in a liquid. Yet, even this compelling model falls short of a complete explanation. The laboratory hexagons are small and transient, while Saturn's version is a planetary-scale giant that has outlasted every human observation. The geometric perfection and sheer longevity of this phenomenon point to forces we still do not fully understand, a fundamental puzzle written in the clouds of a distant world. This rapid spin warps the planet itself into an almost comical shape, the most oblate sphere in our entire solar system. Saturn is so flattened at its poles and bulging at its equator that it looks less like a perfect ball and more like a spinning top someone set down on a table. A day on Saturn is a frantic blur, lasting only about 10.5 hours from one sunrise to the next. This incredible speed, combined with the planet being a fluid ball of gas rather than a solid rock, causes its midsection to fling outward under the immense centrifugal force. Think of a potter spinning a lump of clay, watching it widen and flatten as it rotates faster and faster. Saturn is nature's ultimate demonstration of that principle. But this dizzying rotation creates a profound scientific dilemma. How do you measure the length of a day on a world with no solid surface to track? On Earth, we simply mark how long it takes a mountain to return to the same spot. On a gas giant, scientists must listen for a heartbeat, a regular pulse from deep within the planet. They turn to Saturn's powerful magnetic field, assuming its tilt and rotation would provide a steady, measurable rhythm. The data from the Voyager missions gave one answer, but when the Cassini spacecraft arrived decades later for a more detailed study, it found the magnetic heartbeat had changed. The signal seemed to have slowed down, which is physically impossible for a planet's core rotation. This means the magnetic field is slipping or somehow out of sync with the planet's interior, hiding the true rotation rate. Other methods, like tracking cloud movements or measuring gravity fields, have also provided conflicting numbers. The fundamental length of a Saturnian day remains one of the most basic yet elusive facts about this world, a secret locked within a churning, fluid interior that refuses to give up its rhythm. That dizzying spin and hidden heartbeat point to an even deeper puzzle, one that lies at the very center of the planet. The true nature of Saturn's core remains one of its most profound secrets, a mystery that challenges our most fundamental ideas of how planets are born. For decades, the model was relatively straightforward. Scientists envisioned a layered world with a solid, rocky core at its heart, many times the mass of Earth. This would be surrounded by a deep mantle of metallic hydrogen, a strange, liquid metal form of hydrogen created by immense pressure, and finally, an outer layer of molecular hydrogen gas. This neat, orderly structure was the accepted picture of a gas giant. Then the Cassini mission arrived and turned that picture upside down. During its final, daring orbits, the spacecraft performed a precise gravitational mapping of Saturn. By measuring how the planet's gravity tugged on the spacecraft, scientists could essentially weigh the planet's interior and map the distribution of its mass. The results were shocking. The data did not point to a compact, solid ball of rock and ice at the center. Instead, it suggested a core that is diffuse or fuzzy, spreading out across a staggering 60% of the planet's diameter. This is not a sharp boundary between core and mantle, but a gradual, soupy transition, a mixture of hydrogen, helium, rock, and ice that slowly densifies toward the center. Imagine not a distinct pit inside a peach, but a peach where the densest seed-filled pulp is blended and swirled throughout most of its flesh. This fuzzy core defies traditional planetary formation models, where heavy elements are expected to clump together neatly at the center. It suggests a more violent, chaotic history for Saturn, perhaps a colossal impact in its early days that stirred up the core, or a formation process where it never fully differentiated in the first place. This strange internal structure has dramatic consequences. A diffuse, blended core would fundamentally alter how heat moves through the planet and how its magnetic field is generated, forcing us to rethink the very engine that powers Saturn's magnificent storms and auroras. The heart of this giant is not a simple stone, but a murky, blended enigma that rewrites the story of its creation. While the planet's deep interior churns in secret, its magnificent rings stage their own fleeting performance. Ghostly apparitions sweep across the icy plains, dark and bright smudges that appear as if drawn by an unseen hand. These are the ring spokes, one of Saturn's most transient and beautiful puzzles. They manifest as radial streaks, sometimes stretching over 20,000 kilometers from the inner rings outward, like the spokes of a vast turning wheel. Their behavior is utterly unpredictable. For months they can vanish completely, and then a cluster will suddenly materialize, drift for a few rotations, and fade away just as mysteriously as they came. The Voyager spacecraft first discovered them, and decades later, Cassini watched them reappear as Saturn's seasons changed, confirming they are a cyclical, yet still erratic phenomenon. What force could possibly create these temporary scars on a landscape of orbiting ice? The clues point directly to the invisible forces enveloping Saturn. The spokes seem to form most frequently when the rings are tilted edge onto the Sun during the planet's equinox. This positioning suggests a powerful link to Saturn's magnetic field and the constant stream of charged particles from the solar wind. The leading theory imagines a celestial drama on a tiny scale. Tiny, micrometer-sized dust particles, likely made of silicate rock, lie resting amidst the larger chunks of water ice in the rings. When conditions are right, these specks of dust can become electrically charged, perhaps by plasma from Saturn's magnetosphere or by ultraviolet light from the Sun. Suddenly, these charged dust particles are no longer bound by gravity alone. They experience a powerful electrostatic force, levitating up and away from the ring plane, hovering above or below the main ring layer. From our distant vantage point, this cloud of elevated dust appears as a dark or bright smudge, a spoke that moves under the influence of Saturn's magnetic field, which rotates at a different speed than the ring particles themselves. Yet this elegant explanation has its gaps. The precise trigger for this electrostatic levitation remains unknown. Why do the spokes cluster and appear in specific regions? What determines whether a spoke will be dark or bright against the brilliant ice? The exact recipe of conditions needed to summon these spectral features from the rings remains just out of reach, a subtle interplay of shadow, light, and invisible forces that we are only beginning to perceive. These ghostly ring spokes are a dance of shadow and light, but they are not the only phenomenon drawing energy from Saturn's invisible fields. The planet's atmosphere itself is caught in a thermal mystery, a puzzle of heat where there should be cold. Saturn is much too hot. The upper layers of its atmosphere, high above the cloud tops, are hundreds of degrees hotter than any standard model can explain. This is a planetary energy crisis. Saturn is nearly 10 times farther from the Sun than Earth is, and it receives only about 1% of the sunlight we enjoy. Based on that solar input alone, its upper atmosphere should be a deeply frigid -200 degrees Celsius. Instead, instruments reveal temperatures climbing to a sizzling 800 degrees, as hot as the surface of Venus. Where is all this extra heat coming from? One primary suspect is the planet's spectacular auroras. At the poles, charged particles channeled by the magnetic field slam into the atmosphere, creating brilliant light shows and, crucially, generating immense heat. This heat should then be transported by winds and weather systems from the poles toward the equator, warming the entire globe. Yet, when scientists run the numbers, this auroral heating falls dramatically short. The energy provided at the poles is not nearly enough to account for the widespread, uniform heat observed across the planet's mid-latitudes. There must be another, more pervasive source warming the atmosphere from within. Could the answer lie in the planet's turbulent interior, the churning of its deep, fluid layers, or the slow gravitational contraction of the planet as it cools over billions of years, could be releasing energy that travels upward? Another theory points to atmospheric waves, like immense ripples or vibrations generated by storms far below. These waves could travel upward, carrying energy from the lower atmosphere and depositing it high above when they break, like ocean waves crashing on a shore. This process would act like a giant space heater, warming the upper air from below. However, no single theory has yet been able to fully balance the energy budget. The extreme and unexplained heat of Saturn's upper atmosphere is more than a local mystery. It challenges our fundamental understanding of how gas giants work, forcing us to reconsider how energy moves and is trapped within these colossal, spinning worlds. If we cannot account for the weather on the planet we can see, what does that say about the secrets still hidden within its depths? That unexplained heat high in the atmosphere is a testament to the powerful, invisible forces coursing around Saturn, forces rooted in a magnetic field that is itself a profound oddity. Saturn's magnetic field is an almost perfect symmetrical bubble around the planet, a feature that makes it utterly unique in our solar system. Every other magnetized planet, including Earth and Jupiter, has a magnetic field that is tilted. Our own planet's magnetic north and south poles are offset from its geographic poles, the axis around which it spins. This misalignment is not a flaw. It is a fundamental requirement of the accepted dynamo theory, the model that explains how a planet's magnetic field is generated. A magnetic field is thought to be born from the churning motions of electrically conductive fluids deep inside a planet. This complex, turbulent dynamo needs a certain amount of asymmetry, a bit of a tilt, to operate. It is like trying to start a fire. You need some friction and irregular motion to get the process going. A perfectly symmetrical fluid flow should, in theory, produce no global magnetic field at all. Yet Saturn defies this principle completely. Its magnetic north and south poles are aligned with its rotational axis to within a single degree, a precision that should be impossible. This perfection presents a monumental puzzle. What is happening deep within Saturn's fluid interior to create this symmetrical shield? The answer must lie in the strange, soupy nature of its fuzzy core. One compelling idea is that the very diffuseness of the core, the way the heavier elements are blended and spread out, has a stabilizing effect. Perhaps deep within Saturn, there is a layer where helium is condensing and raining down into the interior. This steady, uniform rainfall of helium could be acting to smooth out the turbulent motions that would normally create a tilted field, effectively suppressing the dynamo's natural tendency to wobble. It would be a layer of remarkable stability, a calm region in the planetary storm that forces the magnetic field into its precise, symmetrical shape. Another, more exotic theory suggests that the dynamo itself is not operating in the deep metallic hydrogen, as it does on Jupiter, but in a shallower, more stable layer of the planet. This unique location, combined with the specific properties of Saturn's interior fluids, might be the key to its symmetrical field. This is not just a scientific curiosity. The strange symmetry of Saturn's magnetic field is a direct window into the hidden dynamics of the planet's heart, a clue that the churning chaos we imagine is, in one crucial layer, a model of perfect and inexplicable order. This perfect symmetry of Saturn's magnetic field seems to stand in stark contrast to another of its polar wonders, one that is visibly transforming before our eyes. The colossal hexagon at the planet's north pole is not just a geometric storm, it is a feature that has changed its very color. When the Cassini spacecraft first arrived at Saturn, the hexagon was a deep, striking blue, a starkly beautiful void against the golden bands of the rest of the hemisphere. But over the course of Cassini's 13-year mission, scientists watched in fascination as that deep blue slowly faded, gradually giving way to a more muted golden haze. The hexagon was losing its distinctive hue. What could cause such a dramatic shift in the appearance of a planet-scale storm? The leading suspect is the slow, relentless march of Saturn's seasons. A single year on Saturn lasts nearly 30 Earth years, and as the planet orbited the Sun, the North Pole moved from the shadows of its long winter into the continuous sunlight of its summer. This increase in solar radiation is thought to have triggered a chemical reaction high in the atmosphere. sunlight acts like a catalyst, breaking down methane molecules and encouraging them to recombine into more complex hydrocarbons, which form a thick, golden photochemical smog. Think of it like a planetary-scale version of urban air pollution, where sunlight reacts with exhaust to create a visible haze. During the long polar winter, this haze likely settled out of the atmosphere, allowing the deeper, clearer blue layers beneath to become visible. But as summer dawned, the constant sunlight began cooking up a fresh batch of this golden haze, filling the hexagon and obscuring our view of the blue depths below. Yet this seasonal explanation, while compelling, is not a complete answer. Why did the color change so uniformly within the hexagon's sharply defined walls? Does the unique wind pattern of the hexagon itself somehow trap this haze, concentrating it inside the six-sided jet stream? Or are there other, more complex chemical processes at work that we have not yet identified? The fading of the hexagon's blue is a quiet, visual testament to the fact that even Saturn's most stable and seemingly permanent features are part of a dynamic, living system, one whose subtle rhythms we are only beginning to perceive. These seasonal transformations of the hexagon are subtle compared to the planet's most violent outbursts. Every 20 or 30 Earth years, Saturn unleashes a storm of such colossal fury that it rewrites the face of the entire planet. Astronomers call these events the Great White Spots, and they are the largest known storm systems in the entire solar system. When one of these monsters erupts, it begins as a brilliant white beacon in the atmosphere, a single churning thunderhead. But it does not stay small for long. With astonishing speed, the storm expands, its turbulent head stretching into a tail of violent weather that races around the globe. Within weeks, this tail of cloud can completely encircle Saturn's entire equator, a belt of tempest over 60,000 miles wide. Imagine a single thunderstorm growing so vast that it wrapped a ribbon of lightning and fury around our entire world, not once but multiple times. The energy released in one of these events is staggering, equivalent to the total energy our own sun radiates into space for an entire year. What internal alarm clock could possibly trigger such a periodic cataclysm? The leading theory points to Saturn's long seasons and its unique atmospheric structure. The planet's upper atmosphere is generally stratified into a warm, light layer over a cooler, heavier one, which suppresses large-scale convection, the process that drives most storms. Over decades, the sun's weak but steady light slowly heats the upper air, allowing moisture to build up. Eventually, the upper atmosphere becomes so heavy and saturated that this stable layering breaks down. It becomes like a pot of water with a lid on it, slowly heating until the pressure becomes too great and the lid blows off. A colossal plume of warm, wet air then punches through from the deep interior, exploding into the upper atmosphere and unleashing a planet-wide tantrum. Yet this seasonal model is imperfect. Why do the storms appear roughly every Saturnian year, but not with precise clockwork regularity? The last giant storm erupted in 2010, decades ahead of the predicted schedule based on previous cycles. This suggests that internal heat bubbling up from the planet's mysterious fuzzy core may play a critical and still poorly understood role. The planet's own internal warmth might be the ultimate fuel, with seasonal sunlight acting merely as the trigger. The Great White Spots are a breathtaking reminder that Saturn is a living, breathing world, holding within its golden haze a pent-up fury that erupts on a schedule we cannot yet predict. A giant's heartbeat written in cloud and lightning. Saturn holds a title no other world can claim, the only planet in our solar system light enough to float. If you could find an ocean large enough to place it in, this colossal gas giant would bob on the waves like a gigantic inflatable ball. Its density is so remarkably low, a mere 6/10 that of water, that it defies our basic intuition about planets. We imagine them as solid, heavy spheres, but Saturn is a world of astonishing lightness. This incredibly low density is a direct window into its composition. the planet is not made of rock and metal in the way Earth is. It is overwhelmingly composed of the two lightest elements in the universe, hydrogen and helium, which exist there in states we can barely replicate on Earth. Think of Saturn not as a solid ball, but as a vast, fluffy atmosphere that gets progressively denser and hotter the deeper you go, with no true surface to stand on. This fact alone presents a profound challenge to our models of how giant planets form. The core accretion theory suggests that planets begin with a solid core of rock and ice that grows massive enough to gravitationally attract a huge envelope of hydrogen and helium gas. If this is true, why is Saturn so much less dense than its sibling, Jupiter? Jupiter is also a gas giant, but it is significantly denser, implying a much greater proportion of heavy elements in its interior, perhaps a more substantial core. This stark difference forces us to question whether the two giants are as similar as they appear. Did Saturn form in a slightly different region of the early solar system, where the protoplanetary disk was less rich in the rocky and icy building blocks needed to create a large, heavy core? Or does its puzzling lightness point to a more dramatic and unique internal history? Perhaps a colossal impact in its youth, the same kind of event that might have stirred its fuzzy core, also blasted away a significant portion of its heavier elements, leaving it with a more gaseous, less dense composition. Another possibility is that its interior is simply more efficiently layered, with the hydrogen and helium remaining more separated, preventing a greater concentration of heavier material from sinking to the center. The fact that we cannot easily explain why one gas giant is so much lighter than the other reveals a fundamental gap in our story of planetary birth. Saturn's ability to float is not just a fun fact, it is a critical clue written in its very being, a whisper from its origins that we are still learning how to decipher. Saturn's delicate F-ring presents a celestial tug of war, a narrow band of ice and dust caught between two competing moons. The tiny, potato-shaped moon Prometheus orbits just inside the ring, while its slightly more distant sibling Pandora travels on the outside. For years, scientists believed these two acted as gravitational shepherds, their gentle, opposing tugs confining the ring material into a neat, stable band, much like two sheepdogs keeping their flock in a tight group. This elegant theory was a cornerstone of our understanding of ring dynamics. Then the Cassini spacecraft arrived and revealed a reality far more chaotic and beautiful than anyone had imagined. Prometheus is not a gentle shepherd, it is a gravitational vandal. As its slightly irregular orbit brings it closest to the F-ring, its gravity does not gently nudge the ring particles. Instead, it violently plunges into the ring's inner edge, carving deep channels and pulling out immense, luminous streamers of ice and dust. Each close pass, which happens roughly every 17 Earth years, creates a new scar, a spectacular filament of material that can stretch hundreds of kilometers across the void. Imagine a sculptor not carefully molding clay, but repeatedly thrusting a hand into it, pulling out long, ragged strands that drape across the studio. The structure these interactions create is not one of orderly confinement, but of constant, breathtaking upheaval. The very forces meant to contain the ring are the ones that continually tear it apart and reshape it. This leaves astronomers with a profound question. Why does the F-ring persist at all? How can it withstand this repeated gravitational assault without being completely shredded and dispersed? The answer may lie in the very chaos we observe. The violent perturbations from Prometheus might trigger collisions and clumping among the ring particles, a process that constantly reforms and reinforces the ring even as it is being torn asunder. The F-ring is not a static monument, but a living, breathing entity, a dance of destruction and creation happening before our eyes, a testament to the dynamic and utterly unpredictable nature of orbital motion. This gravitational chaos in the rings is mirrored by an unexpected stillness in the planet's own skies. High above Saturn's cloud tops, scientists have searched for a familiar feature, the bright, reflective bands of water ice clouds that are so prominent on Jupiter. Yet they find a profound absence. Saturn's upper troposphere is curiously dry, lacking these brilliant white blankets that should by all rights be there. The ingredients are present, hydrogen and oxygen are abundant, and temperatures are cold enough for water vapor to freeze. So where are the clouds? This missing veil points to a fundamental difference in how Saturn's atmosphere churns and mixes. It appears that a powerful, large-scale downdraft is persistently pushing dry air from the higher, colder layers down into the warmer depths, effectively suppressing the formation of these icy clouds. The atmosphere is behaving like a colossal elevator, constantly carrying air that has already had its moisture wrung out back down to the levels where clouds would normally condense, preventing them from ever forming. This creates a drier, clearer upper atmosphere than anyone predicted, forcing a complete rethinking of the weather patterns operating within this golden giant. Compounding this atmospheric puzzle is a chemical mystery. When scientists analyze the light reflected from Saturn, a technique called spectroscopy, they find another glaring absence. The telltale signature of methane gas is far weaker than their models anticipated. Methane should be a stable, long-lasting component of the atmosphere, but something is actively removing it. Is it being dragged down by that same powerful vertical circulation, sinking into the hot, deep interior where it can be broken apart? Or is there an unknown chemical process at work in the upper atmosphere, a hidden reaction that is systematically destroying methane molecules? We know that sunlight can break methane down over time, but the observed depletion is too rapid for photochemistry alone to explain. This suggests the presence of a mysterious sink, a process or a compound we have not yet identified that is actively scrubbing this gas from the sky. Together, the missing water ice and the vanishing methane paint a portrait of an atmosphere that is far more complex and dynamically alien than the seemingly serene bands of color suggest. They reveal a world where hidden currents and unknown chemistry are constantly at work, quietly removing the very things we expect to find. Amidst the chaos of the F-ring, other moons are engaged in a more subtle act of creation and control. Orbiting within the rings themselves are two of the strangest objects in the solar system, Pan and Atlas. These tiny worlds are not spherical like our own moon, nor are they lumpy potatoes like many asteroids. They have been sculpted into bizarre, flattened shapes that look remarkably like flying saucers, or perhaps more appetizingly, like two giant pieces of ravioli floating in the depths of space. Their forms are a direct result of their unique location, nestled within gaps in Saturn's main rings. For countless millennia, these moons have traveled through a blizzard of fine ice and dust. Their gravity gently pulls this ring material toward them, but because the moons are so small and their gravity so weak, the particles do not crash onto the surface with great force. Instead, they settle gently like a soft snow falling on a wide, flat field. This process, called accretion, has slowly built up a thick, smooth equatorial ridge around each moon's middle, giving them their distinctive dumpling-like appearance. They are worlds literally built from their own surroundings, yet their very existence is a puzzle. How did they form in the first place, right in the middle of the rings? Were they always there, the last surviving remnants of a larger moon that was torn apart, acting as a seed around which the ring material gathered? Or did they somehow coalesce directly from the ring particles themselves, a process we thought was impossible in the current era? Their stability is another enigma. The delicate balance that allows them to gather this material without either consuming their entire orbital path or being thrown out of it by gravitational perturbations is a cosmic tightrope act. These flying saucer moons are more than just curiosities. They are active participants in shaping the rings they call home. Pan, for instance, orbits within the Encke gap in the ring. Its gravity does not just collect dust, it acts like a celestial plow, clearing and maintaining the gap itself. As Pan travels, its gravitational pull pushes ring particles away, sweeping a clean path and creating wave-like patterns along the edges of the gap. Atlas, orbiting just outside the Brilliant ring, plays a similar role, its gravity helping to define the ring's sharp outer boundary. These odd little moons are both the product of the rings and their architects, their strange shapes a living record of the endless, gentle snowfall of ice that continues to shape the Saturnian system. The same forces that sculpt flying saucer moons from ice have worked a far greater miracle on the small, icy world of Enceladus. This unassuming moon, no larger than the British Isles, holds one of the most profound discoveries in our search for life beyond Earth. For decades, Enceladus appeared as little more than a bright, frozen marble, the most reflective object in our solar system. Then the Cassini spacecraft witnessed the impossible. Plumes of water vapor and ice crystals were erupting from its south pole, shooting hundreds of kilometers into space. These were not random vents, but a coordinated set of geysers blasting from a series of warm, parallel fractures nicknamed the Tiger Stripes. This was the first direct observation of a liquid water reservoir beyond our own planet. The implications were staggering. Cassini did not just watch these plumes, it flew directly through them, tasting their composition. The analysis revealed a stunning cocktail. The ice grains were laced with sodium and potassium salts, and most tantalizingly, a variety of simple organic molecules. These are the chemical building blocks essential for life as we know it. The source of these plumes was confirmed to be a global, salty ocean, trapped between the moon's rocky core and its icy crust. Enceladus is not a frozen relic, it is an active, water-rich world. This revelation immediately vaulted Enceladus to the top of the list of potential habitats for extraterrestrial life. But this discovery presents a monumental puzzle. Enceladus is a tiny moon far from the sun. It should be a frozen, geologically dead ball of ice. What immense force is generating enough heat to keep a global ocean from freezing solid and to power these spectacular eruptions? The leading theory points to the relentless gravitational tug of war between Enceladus, Saturn, and its neighboring moons. As Enceladus follows its slightly elliptical orbit, Saturn's gravity squeezes and stretches the moon's interior. This process, called tidal heating, generates immense friction and warmth deep within its rocky core. It is like repeatedly and vigorously flexing a piece of soft metal until it becomes hot to the touch. This internal furnace is thought to be what prevents the ocean from turning to ice and may even be driving hydrothermal vents on the seafloor, similar to those in Earth's deep oceans where life thrives in complete darkness. Yet the math remains a subject of intense debate. Is the tidal heating from Saturn's pull alone powerful enough to account for the observed energy output? Some models suggest it is barely sufficient, while others propose that the moon's interior or orbital dynamics are more complex than we realize. Could there be other sources of heat, perhaps from the decay of radioactive elements in its core, adding to the warmth? The ultimate source of the heat that powers Enceladus's life-giving ocean remains one of the most compelling and unresolved questions in planetary science, a mystery that holds the key to understanding whether we are truly alone in the cosmos. The search for water leads us to a moon that presents a cosmic contradiction in black and white. Iapetus is a world of two faces, one hemisphere as dark as fresh asphalt and the other as brilliantly white as freshly fallen snow. This stark division is so precise it looks as though it were painted by a celestial artist, with the dark material perfectly coating the leading hemisphere, the side that always faces forward as the moon orbits Saturn. How can one single world be so violently split in its very nature? The most compelling theory involves a cosmic game of catch and melt. Far beyond the orbit of Iapetus travels a distant dark moon named Phoebe. This outer moon is constantly bombarded by micrometeoroids, knocking tiny particles of its dark, dusty surface into space. Over millions of years, this soot-like dust slowly spirals inward, drifting toward Saturn. Iapetus, on its stately orbit, plows directly through this faint ring of dark debris, collecting it like a windshield gathering bugs on a highway. But then, a clever feedback loop begins. When the dark dust settles on Iapetus's icy surface, it changes the surface's properties. Dark colors absorb heat, while bright colors reflect it. The dust-covered areas begin to warm up in the faint sunlight. This warming is just enough to cause the underlying water ice to sublimate, to turn directly from a solid into a gas without ever becoming a liquid. This water vapor then drifts through the near vacuum and refreezes onto the coldest available surfaces, which are the bright, clean, icy areas on the opposite hemisphere and the higher latitudes. This process, called thermal migration, effectively cleans the dark areas and paints the bright areas even whiter, amplifying the contrast in a runaway cycle. It is a beautifully elegant explanation, yet it fails to fully satisfy. Why has this process created such an extreme, razor-sharp boundary on Iapetus and on no other moon we have ever seen? Other icy moons are dusted with dark material, but none exhibit this perfect hemispheric segregation. There must be something unique about Iapetus that locks this process in place. Some scientists suggest its slow rotation rate, a single day lasting nearly 80 Earth days, plays a crucial role, allowing the Sun to bake the leading hemisphere for extended periods. Others wonder if the Moon's own geology, perhaps a primordial dark surface that kick-started the cycle, is the true key. The two-faced Moon remains a stark, visual enigma, a reminder that even the most logical processes can create results of breathtaking and inexplicable extremity. While Iapetus presents a stark contradiction of dark and light, another of Saturn's moons offers a world of unsettling familiarity. Titan is a place both alien and strangely Earth-like, the only other world in our solar system with a stable liquid cycle on its surface. Yet here, the rivers and rain are not made of water, but of flowing methane. This creates a landscape that is at once recognizable and profoundly bizarre, where the rocks are made of water ice as hard as granite, and the sand dunes are composed of dark, plastic-like hydrocarbons. The methane cycle on Titan mirrors our own water cycle with an eerie precision. Methane evaporates from vast lakes and seas, forms clouds in the dense, hazy atmosphere, and falls back down as a gentle, slow-motion rain, carving river valleys and smoothing the icy plains. But this seemingly complete picture holds a major chemical mystery, one that has confounded planetary scientists for decades. Based on everything we know about atmospheric chemistry, the constant bombardment of sunlight on Titan's methane should be breaking it apart. Over the billions of years of the solar system's history, this process should have converted a tremendous amount of that methane into a different hydrocarbon, ethane. In fact, scientists were so confident in this prediction that before the Cassini mission arrived, they fully expected to find Titan's surface dominated by a global, sludge-like ocean of ethane, hundreds of meters deep. The spacecraft's cameras revealed a very different reality. Instead of a single, planet-spanning ethane sea, Cassini found a world of distinct, localized lakes and seas clustered near the poles, with vast, dry deserts of hydrocarbon sand in between. The total volume of liquid on the surface is only a tiny fraction of what that predicted ethane ocean should have been. So where did all the missing ethane go? This is one of Titan's most persistent puzzles. One possibility is that the ethane is hiding in plain sight. It might be mixed with the methane in the existing lakes and seas, forming a methane-ethane cocktail that is difficult to distinguish from orbit. Another, more intriguing theory suggests that the ethane is draining away. Titan's icy crust may be porous like a frozen sponge, and the denser ethane could be slowly seeping down through cracks and pores, accumulating in a vast subterranean reservoir deep beneath the surface. A third idea proposes that the ethane is not missing at all, but is being transformed. Complex chemical processes on the surface or in the atmosphere could be converting the ethane into the very same complex, tarry hydrocarbons that make up Titan's dark dune fields. This would mean the missing ocean of ethane has, over eons, literally paved the deserts we see today. Each of these explanations has its own complications, and the true fate of Titan's ethane remains an open case. This missing hydrocarbon forces us to question the very timeline of Titan's atmosphere and the completeness of our understanding of its active, organic chemistry. Tumbling through the void in a state of perpetual confusion, the moon Hyperion looks less like a world and more like a cosmic pumice stone. Its surface is a nightmare of deep, dark pits and sharp, ragged ridges, a spongy texture so extreme that it seems impossible for a celestial body to hold itself together. This is not the result of gentle processes, but of sheer violence. Hyperion is a survivor, a fragment of a much larger moon that was shattered by a catastrophic impact in the distant past. The debris from that collision coalesced, but it never packed together tightly, leaving Hyperion with a density so low it is mostly empty space, a loose pile of rubble barely held by its own meager gravity. You could almost kick a football clean through one of its giant pores and out the other side. This fragile structure explains its appearance, but it creates an even more baffling mystery: its rotation. While every other major moon in the solar system has settled into a predictable, synchronous spin, forever keeping one face to its planet, Hyperion is a chaotic tumbler. There is no North Pole, no regular day and night cycle. Its axis of rotation wobbles so wildly and unpredictably that its future orientation cannot be calculated. One moment its strange, cratered face is pointing one way, the next it has flipped and turned in a completely different direction. It is a moon that cannot make up its mind. This bizarre behavior is a direct result of its irregular shape and its orbital dance. Hyperion is locked in a gravitational resonance with the much larger moon Titan. Every time the two moons pass each other, Titan gives Hyperion a significant gravitational kick. Because Hyperion is not a perfect sphere, these kicks do not nudge it consistently. They act on its asymmetrical form like a series of random pushes on a lumpy, misshapen top, sending it into an endless, drunken stumble through space. The porous structure amplifies this chaos as the gravitational forces act on a body that is more void than substance. The deeper puzzle is how this state has persisted. Over millions of years, the internal friction from such a wild tumble should have dissipated the chaotic energy, slowly damping the wobble until the moon settled into a stable rotation. The fact that it remains chaotic suggests that the tumbling is being actively driven, its strange dance continuously fueled by the precise timing of its encounters with Titan. Hyperion stands as a unique celestial oddity, a world shaped by destruction and kept in a state of perpetual, unpredictable motion by the gravitational rhythms of its siblings, a stark reminder that even in the clockwork of orbits, true chaos can find a home. Even the faintest of Saturn's rings can hold a secret of stunning clarity. Far beyond the main bands of ice lies the wispy, ethereal G-ring, a diffuse halo of dust so faint it was one of the last to be discovered. Yet within this delicate haze, astronomers found something that should not exist, a single, brilliant arc of materials shining like a solitary strand of pearls against the void. This is not a complete ring, but a partial one, a tightly confined ribbon of ice dust particles that refuses to spread out and blend into the faint background of the G-ring. How can such a structure persist, a dense river of dust flowing through an otherwise sparse cloud? The answer was found orbiting within the arc itself, a tiny, secretive moon named Aegeon. This minuscule world, likely no more than a kilometer across, is the shepherd of this luminous band. Its gravity is the dominant force within this region, but the puzzle is how such a small moon can exert such precise control. The solution lies in a delicate celestial dance, a gravitational resonance with the much larger moon Mimas. Mimas, the moon that famously resembles the Death Star, orbits farther out, and every time Aegion completes a certain number of orbits, it finds itself in the same alignment with Mimas. This repeated alignment gives Aegion's gravity a periodic boost, a consistent nudge that acts like a shepherd's crook, corralling the fine dust particles and confining them to a narrow path. It is a cosmic version of pushing a child on a swing, where small, well-timed pushes can build into a large, controlled motion. Yet this elegant explanation only deepens the mystery. Resonances are common in the solar system, but they typically disperse material, not gather it. The precise mechanism that allows this gentle, resonant forcing to overcome the natural tendency of the dust to drift apart remains a dynamic puzzle. Why don't collisions or the faint pressure of sunlight blow this delicate arc apart? The particles within the arc are incredibly fine, like microscopic shards of glass, and their interactions with each other and with the faint magnetic fields that permeate space are poorly understood. The G-ring's bright arc is a testament to an exquisitely balanced system, a fragile structure that exists only because a dozen different forces are in a perfect and perhaps temporary equilibrium. It is a whisper of order within the chaos, a single, luminous note held in a gravitational harmony we are only just beginning to hear. Even within the ordered beauty of Saturn's main rings, there are whispers of hidden worlds. Scattered throughout the brighter ring are thousands of strange, propeller-shaped features, each one a unique signature carved into the ice by an unseen force. These are not full-fledged gaps like the one cleared by the moon pan, but rather partial voids, a pair of delicate, curving slits that spiral out from a central point, resembling the blades of an antique airplane propeller frozen in the void. Each one is a cosmic footprint, evidence of a hidden moonlet, a tiny world too small to be seen directly, yet large enough to make its gravitational presence known. These embedded moonlets, given names like Blériot after aviation pioneers, are thought to be no more than a kilometer across. Their gravity is too weak to sweep a clean path through the ring, but it is perfectly tuned to gently push the surrounding ice particles aside as they orbit, creating these beautiful, temporary scars in the ring plane. They are the ghosts in the machine, felt but never seen. Their very existence presents a triple mystery. Where did these propeller moons come from in the first place? Are they the shattered remains of a larger, disrupted moon, the last surviving building blocks of a world that never was? Or are they primordial, ancient shards that have been orbiting within the rings since the system's violent birth, acting as seeds around which the finer ring material gathered? Their number is another enigma. Cassini discovered they are far more numerous than anyone predicted, suggesting a vast, hidden population of these tiny worlds lurking just beneath the resolution of our cameras. This raises profound questions about the ring's composition and mass, hinting that there may be more solid material embedded within the icy dust than we ever imagined. But perhaps the most intriguing puzzle is their ultimate fate. These propeller moonlets are caught in a gravitational tug of war. Their constant interaction with the ring particles should, in theory, cause them to slowly lose energy and drift inward toward Saturn, like a pebble slowly sinking in a pond. Yet, many of them seem to be holding their ground. Some appear to be locked in resonant orbits with larger, more distant moons, their positions stabilized by the same kind of gravitational harmonies that create the G-ring's arc. Others might be migrating, their propellers leaving a faint trail as they move, a journey we have only just begun to track. Are we witnessing the slow death of these tiny moons, or are they finding a way to survive within the dynamic chaos of the rings? Each propeller is a fleeting monument to an unseen world, a delicate balance between creation and destruction happening on a scale we are only beginning to perceive. That very question of survival returns us to the most fundamental mystery of all, the age of Saturn's rings themselves. Are we witnessing a temporary spectacle or a permanent feature of the solar system? The debate over their birth date is more heated than ever, with compelling evidence pointing to two wildly different timelines. On one side, the rings appear impossibly young. Their breathtaking brightness is the key clue. The rings are made of more than 95% pure water ice, reflecting sunlight with a brilliant, almost sterile whiteness. This pristine condition is a serious problem for an ancient origin. The space between planets is not empty, it is filled with a constant, fine rain of meteoroid dust, dark and sooty material. If the rings were as old as Saturn itself, over 4 billion years, this relentless bombardment should have polluted them, turning their brilliant white into a murky, dark gray. Their clean, icy shine strongly suggests they have not been subjected to this cosmic pollution for very long. The calculated rate of contamination points to a surprisingly recent origin, perhaps as young as 100 million years, a time when dinosaurs still roamed the Earth. This is a blink of an eye in the 4.5 billion year history of our solar system. Yet this youthful appearance is fiercely contested. Could the rings be primordial, formed with Saturn, but somehow managing to stay clean? Some dynamical models suggest processes that might actively cleanse the rings or recycle their material. Perhaps the rings are not a static structure, but a constantly renewing system. When micrometeoroids strike the rings, they don't just leave a dark stain. They can vaporize ice, creating a tiny puff of water vapor that then recondenses into a bright, new, clean ice particle. This constant churning and refreshing could be like a self-cleaning oven, keeping the rings looking young even if they are truly ancient. Another possibility is that the rings are much more massive than we currently estimate. A heavier ring system would be better at absorbing dark contaminants without showing a significant change in its overall brightness, effectively hiding its true age. However, measurements of the ring's mass from the Cassini spacecraft support the younger age theory, suggesting they are too lightweight to have weathered billions of years of bombardment. This leaves us with a beautiful and profound dilemma. We are forced to choose between the ring's youthful appearance and the immense statistical improbability of us being lucky enough to exist in the brief cosmic window when Saturn wears its crown. The true age of the rings remains an open question, a puzzle written in pure light and ancient ice, waiting for a future mission to finally weigh the evidence and decide if we are witnessing a fleeting marvel or an enduring giant. Far above the planet's churning clouds, another light show defies all our earthly expectations. Saturn's auroras blaze with an eerie, majestic beauty, but their behavior is alien to everything we know from our own polar skies. On Earth, the northern and southern lights are transient curtains of color, dancing and shifting in direct response to the gusting solar wind. Saturn's auroras, however, possess a strange, independent life of their own. While they are still ignited by the impact of charged particles, their ultimate driver is not just the sun. The planet's own frantic rotation, a complete spin every 10.5 hours, whips its magnetic field into a frenzy, generating electrical currents that can power the auroras from within. This creates displays that can persist for days, immense ovals of glowing hydrogen that crown the poles with a steadfast, haunting luminescence. Even more puzzling is their rhythm. Unlike the chaotic shimmer of Earth's lights, Saturn's auroras have been observed pulsing with a remarkably regular beat, flaring up brightly every 45 minutes or so with the precision of a cosmic metronome. What internal clock could possibly keep such perfect time? Scientists suspect this pulse is tied to the planet's mysterious symmetrical magnetic field. The steady rotation of the field itself may be creating waves of energy that travel along magnetic field lines, periodically dumping bursts of particles into the upper atmosphere and causing the auroras to flare in sync. Another theory points to a sloshing motion of plasma within the vast magnetosphere, a great wave that washes against the planet's magnetic shores with a predictable regularity. Yet, no single model fully accounts for the persistence, the location, and the precise cadence of these pulsing lights. They are a visible symptom of the hidden, complex dance between Saturn's deep interior, its powerful magnetic field, and the constant flow of energy from the Sun, a dance whose steps we are only beginning to learn. The deep, reddish blackness smothering Iapetus is a cosmic stain, one that leads our investigation millions of miles outward to its suspected source. The distant moon Phoebe is a dark, captured world, a wanderer from the outer solar system that Saturn's gravity imprisoned long ago. Its surface is coated in the same mysterious, ruddy material that paints Iapetus, a substance that behaves almost like celestial soot. The elegant theory connecting them is one of the most compelling stories of transfer in the solar system. Micrometeoroids constantly pelt Phoebe's surface, blasting this dark dust into space where it slowly spirals inward toward Saturn, creating a vast, invisible ring of fine particles. Iapetus, on its unwavering orbit, then flies directly through this debris stream, its leading hemisphere acting like a giant dust collector, gathering the dark coating over countless millennia. It is a beautifully simple chain of cause and effect, a celestial painter and its canvas. Yet, for all its elegance, this explanation may not be entirely sufficient. The sheer efficiency required for this process to create the extreme, pitch-black darkness of Iapetus is staggering. Could a faint ring of dust originating from a relatively small moon so far away really deliver enough material to create such a profound and perfectly confined stain? Some calculations suggest the process is too slow, that there simply hasn't been enough time or enough dust from Phoebe alone to account for the dramatic coverage we observe. This forces a difficult question. Is Phoebe the sole source of this dark material, or merely one contributor to a more complex phenomenon? Perhaps Iapetus itself is partly responsible for its own two-faced nature. Maybe ancient cryovolcanoes on the moon once spewed dark, organic slush onto its surface, providing a seed that the incoming Phoebe dust then amplified through the thermal migration process. Another possibility is that the material comes from multiple sources, a mixture of Phoebe's dust combined with dark compounds created in situ by the relentless bombardment of cosmic rays and ultraviolet light on Iapetus' own surface ices. The connection between Phoebe and Iapetus is likely real, but the absolute darkness of that one hemisphere suggests a deeper, more intricate recipe is at work, one where internal geology and external painting combine to create one of the most visually striking puzzles in the Saturnian system. This gravitational harmony governs the motions of entire worlds. Orbiting deep within Saturn's inner moon system, Mimas and Tethys are locked in an exquisite celestial duet, a perfect orbital resonance. For every single orbit that Tethys completes, the smaller moon Mimas completes precisely 2. This simple 2-to-1 ratio means their gravitational dance repeats with clockwork regularity, a predictable rhythm that has likely persisted for billions of years. Such resonances are the great architects of planetary systems. The consistent periodic tugs between moons prevent their orbits from drifting randomly. Instead of a chaotic jumble, these gravitational nudges create stable, repeating patterns, clearing out zones and sculpting the overall structure of the satellite family. The existence of this resonance is not the mystery, but its origin is. How did these two specific moons fall into such a perfect, long-lasting lock? The leading theory suggests a gentle, gradual migration. In the early solar system, the moons likely formed farther from Saturn and have been slowly drifting inward ever since, pushed by tidal interactions with the planet itself. As they migrated, their orbital speeds changed. At some critical point in this ancient drift, Mimas and Tethys crossed into their resonant configuration, their gravitational influences snapping into a mutual embrace that has held firm ever since. Yet this explanation only deepens the puzzle. Orbital resonances are powerful, but they are also delicate. They can be easily broken by close encounters with other moons or by significant impacts. The fact that this 2-to-1 lock between Mimas and Tethys has survived the violent, chaotic early era of the solar system suggests the system of inner moons has been remarkably stable and undisturbed. This specific, pristine resonance acts as a silent witness, a preserved record pointing to a surprisingly calm and orderly formation for this part of Saturn's domain. It implies that these moons have been dancing their precise two-step waltz since almost the very beginning, a timeless rhythm that holds untold clues to the infancy of the entire Saturnian system. These pristine gaps in the rings are not all empty by accident. The Cassini division, that stark, dark band separating the A and B rings, is a perfect example. It looks like a cleanly swept path through the glittering ice, yet no shepherd moon is there to be seen, no obvious gravitational custodian keeping the lane clear. So what invisible hand maintains this order? The answer may lie not in a single resident moon, but in a distant, rhythmic tug. The gap aligns perfectly with a powerful gravitational resonance with the moon Mimas, which orbits much farther out. For every 2 orbits a ring particle in the Cassini division makes around Saturn, Mimas completes exactly 1. This 2-to-1 rhythm acts like a celestial metronome, delivering a consistent, repeating gravitational kick to any particle that dares to wander into the zone. Over time, these accumulated nudges are enough to push the material away, effectively clearing the region and preventing new ice from settling in. It is a case of remote control, where a moon never needs to visit a place to dictate what happens there. But not every gap has such a clear and powerful patron. For many other sharp edges and empty lanes within the rings, there is no obvious moon, large or small, to account for their existence. This has led scientists to propose a hidden population of tiny, unseen moonlets, too small for our cameras to resolve, yet possessing just enough gravity to sweep their immediate vicinity clean. Think of them as miniature custodians, each one maintaining a small section of the grand structure. Their collective, invisible work could be what carves and preserves many of the ring's most intricate features. There is also the possibility of temporary or partial resonances, where the gravitational influence of a larger moon is just strong enough to create a boundary for a time, or where the combined gravity of many small, embedded objects creates a stable void. The very sharpness of these gaps is a clue that the process maintaining them is ongoing and remarkably precise. The rings are not a static photograph, they are a dynamic ballet, and these empty spaces are the choreographed pauses, held in place by forces we are still learning to see. This slow but steady cascade of ice is known as ring rain. High above the cloud tops, charged ring particles, influenced by Saturn's magnetic field and the Sun's gravity, are funneled downward in a perpetual, silent shower. The rings are actively disintegrating, bleeding their substance back into the planet they orbit. Measurements suggest this downpour is substantial, draining an Olympic-sized swimming pool worth of water from the rings every single day. On a cosmic timescale, this is a death sentence. If this rate of loss has been constant, some estimates suggest the magnificent rings could be completely gone in another 100 million years. We are left with a breathtaking and humbling possibility. Not only might Saturn's rings be a recent addition to the solar system, but they could also be a transient one, a glorious spectacle that appears and vanishes within a cosmic blink. This creates a profound temporal puzzle. If the rings are both young and ephemeral, what incredible event occurred so recently to place this crown upon Saturn, only for it to now be fading before our eyes? The violence needed to shatter a moon or disrupt a comet feels too immense to have happened in what is essentially the present day, a time when mammals already dominated the Earth. The alternative is equally puzzling. Could the ring rain be a temporary phase, a symptom of the rings being in a particular state that accelerates their loss? Perhaps there are replenishing mechanisms we have not yet seen, hidden sources of new ice from within the ring system itself or from the slow erosion of its embedded moonlets. The ultimate fate of the rings is inextricably linked to their origin, and both remain shrouded in uncertainty. To witness them is to behold a masterpiece that is both brilliantly young and fading before us, a reminder that the universe is not a static museum, but a theater of constant, beautiful, and mysterious change. From its fleeting rings to its two-faced moons, Saturn is a world built on enigmas. We have journeyed through 25 of its deepest secrets, from the impossible geometry of its polar hexagon and the hidden rhythm of its fuzzy core, to the ghostly spokes that sketch its rings and the unexplained heat that warms its skies. We have witnessed the life-giving plumes of Enceladus and the methane seas of Titan, the chaotic tumble of Hyperion and the silent reign of the rings themselves. Each mystery, from the planet's puzzling lightness to the perfect symmetry of its magnetic field, is a question without a definitive answer. These are not mere curiosities. They are fundamental challenges to our understanding of how planets form, how they age, and what it means for a world to be alive. Every unexplained phenomenon is a beacon, a signal that there is so much more to learn, driving the design of new missions and the creation of new technologies. The greatest legacy of Saturn is this enduring sense of wonder, the knowledge that our solar system still holds profound secrets waiting just beyond our grasp. So we turn this final question to you. Which of these 25 mysteries captures your imagination the most? Is it the potential for life in a hidden ocean, or the cosmic violence that carved a crown of ice? Let us know your thoughts, and if you want to continue exploring the wonders of our universe, be sure to subscribe for more deep dives into the cosmos.